In the last lesson, we learned about new classifications for numbers as either rational or irrational. Anything that is either irrational or rational is going to be part of what's called the set of real numbers. Why do we call them real numbers? Well, because there's something that's called imaginary numbers. These are ones that are mathematically impossible. Like if I try to put the square root of -2 in my calculator, no number multiplied by itself is ever going to equal a negative, so my calculator is just going to say error, and that's going to be mathematically impossible as we understand it. If it's mathematically possible, then we consider that a real number. So some of the classifications for numbers you should already know are natural numbers, which we represent with a capital N, where it's just 1, 2, 3, 4, going on and on and on, where it's positive numbers with no decimals, no fractions. Whole numbers, which is represented with a W, adds the value of 0. 0 didn't always exist as a concept. That was actually an absence of number, but now we use the number 0, so that makes it a whole number. If I go to integers, there's still no decimals or fractions, but I add all of the negative possibilities, and that's represented with a capital I. If it is positive or negative, but can still be represented as a fraction, we call that rational. If it is positive or negative but can't be represented as a fraction, where it's non-terminating and non-repeating, we call that irrational. Rational is represented with a capital Q, and irrational is a Q with a line over it. Like I said, anything that is either rational or irrational is a real number. That's any number that can mathematically exist as we understand it, and real numbers, we use a capital R to represent them. So, because a number can be part of multiple categories, we have this nesting diagram that we use, where we start with natural numbers in the middle, and then it goes to whole numbers, and then it goes to integers, then to rational numbers, and if it's none of these things, then it is a irrational number, as long as it can mathematically exist. Noting that there is a dividing line in between here. We create it so that it's nesting because if it is part of an inner circle, like natural numbers, then it's also part of all of the ones that are outside of it, with the exception of rational numbers. Any natural number is also a whole number, an integer, and a rational number. Any whole number isn't natural, but it's still an integer or a rational. Any integer is still a rational number, but it's not necessarily whole or natural. So there's the primary classification we use, and then there's all the other classifications that it fits under. The primary classification is the smallest group that it fits into, remembering that the smallest is natural, then whole, then integers, then rational numbers, then real numbers. So, if I'm trying to classify a number, 9 is positive, it's not 0, and it's not a decimal or a fraction, which means 9 is natural, whole, integer, rational, and real. 11 over 7 is going to be a rational number and also a real number. The square root of 5 is irrational, but it's still a real number. And -7 is an integer first, because it's not positive, but it's not a decimal or fraction, but it's still rational, and it's still a real number. Now, when it is asked why 9 belongs to 5 number sets, but -9 belongs to only 3 number sets, it's because negatives are not natural or whole. So there's those two categories, even though it doesn't have a decimal in it. There's those two categories that separate it, natural and whole. All right, if we're talking about square roots, all positive numbers have two square roots, one positive and one negative. The positive square root is called the principal square root and is denoted by the symbol of just the square root sign. The square root of a perfect square are always going to be rational numbers. So the square root of 16 is going to be 4 or -4. The square root of a non-perfect square is always going to be irrational. So the square roots of 17 are square root of 17 or the negative square root of 17. I can't represent it as other values because I'm going to have to round or do something like that. So it's not going to be the exact value. Now, when it says estimate mentally, you don't have to estimate. That's not something I'm ever going to ask you to do on a test. All you have to do is plug it into your calculator and do a reasonable approximation of what it is. In this case, we're going to state what it is to the 10th. The more important thing is, do you know how to correctly plug these different things into your calculator to get their actual values? If I take the square root of 46, then the square root of 46 is going to be approximately 6.8. If I take the 2 times the square root of 18 plus 5 times the square root of 37, then that's going to give me approximately 38.9. The negative square root of 5, noticing that the negative is outside of the square root, so this is possible, is going to be negative 2.2. And the square root of the square root of 95, you're going to have to either plug it in twice in your calculator, so the square root bracket 95, or you're going to have to take the square root of 95 and then take the square root of that answer, and that's going to give you approximately 3.1. Remembering, you don't have to estimate, so don't worry about that. You could plug these into your calculator and find what it is to one digit. If I'm doing cube roots, then the cube root of a perfect cube is going to be a rational number. So the cube root of 1000 is exactly 10. And for cube roots, because it's something multiplied 3 times, you can take the cube root of a negative number. That's the difference between a square root and a cube root. In fact, any odd root, so a cube root, a fifth root, a seventh root, you can always make it of negative. Any even root, square root, fourth root, sixth root, it's not possible. The cube root of a non-perfect cube is always going to be irrational. So if I took the cube root of 9, then it's just going to stay the cube root of 9 because it's going to be a non-repeating, non-terminating decimal that goes on forever. The only way I can properly represent it is as the cube root of 9, and just leave it like that. Once again, don't estimate. Just make sure you know how to plug into your calculator. If you're on a TI 83 or 84, you got to go under the math functions for the cube root of these things. If you're on a different calculator, typically it's going to be the x root of y is what you're looking for to plug it in. And when I take the cube root of 11, then to the nearest tenth, I get 2.2. If I take the cube root of 120, I get 4.9. And if I take 4 times the square root of 70 minus 4 times the cube root of 70, I get 17.0. We're going to take a quick look at the extension. You're not going to be tested on this, but it is going to be something that is going to come up for grade 11. When we're talking about the absolute values, an absolute value of a real number is defined as the principal square root of the square of whatever that number is. So if I took 6 and I squared it, I get 36. If I take the positive square root of 36, I get 6. If I took negative 6 and I squared it, negative 6 times negative 6 is positive 36. If I take the principal or positive square root of 36, then I'm also going to get 6. So the square or absolute value is going to be written where I have these two lines on either side of whatever the value is, which means I'm just taking the positive version of that number. I can also represent it in terms of a distance. What is the absolute value of 6? It is the distance between 6 and 0, which is going to be 6 units. What is the absolute value of negative 6? It's the distance between negative 6 and 0, which also happens to be 6 units. If I was to graph the inequality, the absolute value of a variable is less than 4, then the distance from 0 must be less than 4 units, which means that I could either go 4 units to the right or 4 units to the left. And it's going to be everything that fits in between negative 4 and positive 4. So if I'm evaluating this, I'm going to say the absolute value of negative 7 is positive 7, plus the absolute value of 7 is 7. This would give me 14. 1 minus 5 is going to give me negative 4, and when I take the absolute value of negative 4, it becomes positive 4. For this one, I'm taking the negative absolute value of the negative of the square root of 81, which is 9. The absolute value of negative 9 is going to become positive 9, and I'm going to change, when I take the absolute value of this, change the absolute value brackets into regular brackets, because I still need to apply this negative coefficient on the outside, and it's going to wind up being negative 9 again. If I'm stating the absolute value in this case, and I'm looking at it in terms of the distance of 0, then it could either be to the right 3, or it could be to the left 3, which means that the absolute value of A has to be less than or equal to 3, because it can be up to 3 or less than that. When I take a look at the second one, then the distance from 0 is 4 to the right or 4 to the left, but it wants the number to be bigger than whatever that is, which means that this would be the same as saying the absolute value of A has to be greater than, we don't include equal to because it's an empty dot, 4. So I'd go 4 to the right, and then it has to be greater than that. I would go 4 to the left, and it has to extend beyond that. Remember, these extension questions are not a requirement. It's just something that's going to come up in grade 11.